Okay, so last time we talked about acids and bases, and we talked about sort of pH, H plus, OH minus, KW, all that kind of stuff there. So let's just talk a little bit about some of that stuff we touched upon. Um, remember, sort of an acid, sort of the definition of an acid was that we oftentimes think about is the Bronsted-Lowry definition. And that Bronsted-Lowry definition of an acid is something that will donate an H plus. And again, a Bronsted-Lowry base is something that will accept an H plus. Remember, as we talked about as well in sort of this acid base chapter, H plus, H3O plus, essentially equivalent to each other, used interchangeably both in equations and formulas as well. We also had our conjugate acid-base pairs as a result of the Bronsted-Lowry definition. The difference between those guys, as we talked about, is basically just one H plus difference. So in order for something to be sort of an acid conjugate base pair, they should only differ from each other by only one H plus. If it's more than one H plus, then again, they are really not pairs. So a reminder as well that in terms of where we find these guys, acid over here on our reactant side, base on our reactant side, and then typically our conjugate acid and conjugate base there on the product side. Again, the relationship acid on one side, partner on the other side, conjugate base, and vice versa there, base and conjugate acid. Again, only one H plus difference between those two. And again, that was what will make them sort of pairs. We also talked about sort of how we could determine if a solution is acidic, basic, or neutral. There's several different ways to do that. First way we talked about was sort of using what's referred to as KW, which is the equilibrium constant for water. And that is H plus times OH minus is equal to 1 times 10 to the minus 14. Again, you can use that to solve for either the H plus or the OH minus concentration. Again, they're really the same calculation regardless of which one you're doing. You're basically going to take 1 times 10 to the minus 14 divided by the other's concentration. And the relationship between H plus and OH minus is sort of an opposite one. As one goes up, the other goes down. So there's sort of that up and down sort of relationship between H plus and H plus and OH minus that happens. Obviously, the H plus is our acid part of the solution, OH minus sort of the base part of the solution. So if you do this calculation, the H plus is larger than the OH minus, then you would assume it's acidic. If the H plus equals the OH minus, then they both will be 1 times 10 to the minus 19. It will be neutral. And if the H plus is less than the OH minus, then it will be basic in that particular case. We also talked about the pH scale, which runs from 0 to 7 to 14. Above 7 is basic, below 7 is acidic, and 7 there is neutral. And again, as you go kind of from 7 to either direction, either become more basic as you head towards 14 or more acidic as you head towards 0. We could calculate the pH by taking minus the log of the H plus concentration. We also talked about a similar scale that deals with POH or OH minus concentration, and that's what's referred to as the POH, which is minus the log of the OH minus concentration. The nice relationship between those two is pretty much if you add them together, you get the pH scale of 14, basically. So that gives you some options in terms of how to solve some of these problems. It may make more sense to go with the pH first, or maybe the POH first, and sort of subtract off 14 to do that. Now, we also talked about that if you do have the pH value given to you, you could calculate the H plus concentration by taking the inverse log of the minus pH. And again, on most people's calculators, when you hit the inverse log, which is really the second or shift button top left corner, most calculators usually pop up a 10 and a caret and then negative pH. You could also do that with our POH as well. OH minus concentration would be the inverse log of the minus POH. Again, popping a 10 and a caret up, POH would get you there. Remember, in terms of significant figures, the number of decimal places in a pH or POH value equals the number of significant figures in the concentration value. So we go from sort of sig figs to decimal places when we're dealing with calculating pH or POH. We also go backwards. So if you're starting with the pH or the POH, it has 2 decimal places. Your concentration should end up with 2 significant figures. Any questions on all that stuff that we talked about there last time? Okay, so we really did finish up, I think, last time doing a couple of examples where it wasn't just a sort of generic, here's the H plus concentration, or here's the OH minus concentration, in sort of a generic form. We were actually given some strong acids or strong bases. So remember that strong acids are strong electrolytes. And what that means is that when they are in solution, they 100% break apart. So when you have a strong acid, which is basically a strong electrolyte, in that solution, you no longer have any of the whole units of that acid still together. You have 100% of the ions floating around, which basically means you have 100% of the H pluses floating around and whatever the other part of it is. And that's why it's considered a strong acid, because it generates a lot of H plus very quickly. And that's different than a weak acid, which is a weak electrolyte and mainly stays together. But does produce a few ions present. But because it's able to produce a few ions, there's a little bit of H plus floating around. It is still considered an acid, but nowhere near obviously a strong acid, because it's not generating as much H plus or free H plus. Bases work the same way. You really kind of the same deal. So we'll just go like that, and base as well. So here's a few sort of strong acids. When we look at some of these guys, is perchloric acid, hydrochloric acid, hydrobromic, hydroiodic, nitric, and sulfuric. These are some really some strong acids that we come across a lot. Here's some of our strong bases. A lot of our strong bases contain hydroxide in it. And if you sort of look at the periodic table, this is really your group 1 and group 2, right? Group 1 here, group 2 over here, basically. And in fact, if you start in group 1 and kind of do this and make a right at potassium and then go down, that's pretty much your strong bases there in group 1 and 2. In terms of that, that's potassium right about there. And that would be calcium. So you kind of go down like that. And that's where a lot of our strong bases really do come from. To deal with, if you are given sort of a strong acid or strong base and you're asked to calculate the pH of it, really in terms of pH, you just need to sort of figure out what is the H plus concentration if you have a strong acid, and what is the OH minus concentration if you have a strong base. That will allow you to get to the POH and then to the pH as a result of that. In most cases, or a lot of cases, is sort of a one-to-one relationship between the whole thing and H plus or OH minus. So it's kind of the same concentration. Although one of the examples we did, I think it might have been calcium hydroxide, because it did break apart into 2 hydroxides. You did need to adjust the concentration of OH minus in order to get the proper one to use for the POH. Any questions on any of that stuff there? Okay, then since we started talking a little bit about strong acids here, we will talk about now what we do with weak acids and how we sort of deal with those type of problems. So when we do have a weak acid, because it's really a weak electrolyte, it is not going to 100% break apart. It's going to basically stay together and set up this equilibrium. So if this is just a generic here, monoprotic acid, monoprotic means it has one H plus to give. And we could show the dissociation. And again, the difference between these two reactions or equations is one is using water in terms of the acid dissociation, which gets us our H3O plus. The other one, no water, gets us the H plus. Again, either one is perfectly fine. But when it does set up this equilibrium, that means that we will have an equilibrium constant associated with this, and we can write it. And it is what is referred to as Ka for like acid, right? So this is the Ka value. And it's the same equilibrium as we've done before. It's our products over reactants. Again, we would not include anything like water in it or a pure liquid. So even if you wrote the top equation, you would leave this guy out of it, and the Ka expression for the top guy, which is basically equivalent to the one that's on the screen, would look something like this here. So this one here and this one here, again, pretty much equivalent to each other. A weak acid will have a Ka value. And again, it's really just an equilibrium constant like anything else. The relationship here in terms of the Ka is as the Ka value increases, the strength of the weak acid also increases. So you might be asking what that means. So it means that essentially the same idea as when we talk about when we have a large value of K, an equilibrium constant. That means when we reach equilibrium, we mainly have products present. And if we mainly have products present in this situation, which it would mean the same, we have mainly these guys. And if we have mainly these guys on the product side, we have a lot of free H plus that's there. And because we have a lot of free H plus, that makes it a stronger weak acid. And that's an important distinction there. It makes it a stronger weak acid. So in comparisons of one weak acid to another, when you look at the Ka values, the one with the larger Ka value is the stronger, again, weak acid. All weak acids are obviously weaker than a strong acid. So even the strong weak acid, as weird as that might sound, is obviously weaker than a traditional strong acid like hydrochloric acid. And again, the reason is very simple. Something like hydrochloric acid, which is a strong acid, it is a one-way street, and it is 100% breaking apart here and producing a lot of H plus very quickly. This guy's can go back and forth and not obviously be able to produce as much H plus as something like hydrochloric acid. Thus, it is obviously a weaker acid than something like hydrochloric acid. Any questions on that there? So, does strong acids have Ka values? So think about that for a second and think about, would you expect a strong acid to actually have a Ka value? And hopefully the answer that you would come to is the answer is no, right? A strong acid like hydrochloric acid, because it's a strong electrolyte, pretty much is a one-way street, which means it is 100% going to the product side. There is no back and forth, right? As opposed to a weak acid like hydrofluoric acid or something like that. It is a back and forth equilibrium that will occur, and they be able to obviously have an equilibrium constant. So strong acids typically do not have equilibrium constants. The only one listed that you might see in a Ka table is H2SO4, and that's because It's a strong acid, but it's a diprotic acid, so it actually has 2 hydrogens. And the second part of that, the HSO4 minus, is sort of a weak acid. What you'll see listed for something like sulfuric acid for the first H is it's really large, so it's not a very much of a value or number that you see. So typically strong acids would not have a Ka value. Ka values are really only reserved for weak acids. So what does that mean? It means that if you see a Ka value associated with an acid, you should know it's a weak acid. And that's a good way, to kind of figure those things out. So if you can find it on a table, obviously a Ka table, you'll know it's a weak acid because of that. Any questions on that there? So strong acids, no Ka values because they do not set up an equilibrium. They 100% break apart into ions. Now, how do we go about figuring out the pH of a weak acid? Well, the pH of a weak acid can be figured out pretty much with an ice table. So because it's an equilibrium, because it's a weak electrolyte and it sets up that equilibrium condition, we could simply do an ice table here to figure out the pH. So what would we be interested in the ice table? Well, if we look at the equation above there where we have our acid here, break it apart into our H plus and A minus in this particular case. And we do our ice table here, our whatever number we have, 0, 0, minus X, plus X, plus X. Number initially minus X, X, and X. What we're really interested in, instead of a sort of traditional equilibrium problem where we're maybe interested in everybody's concentration here at equilibrium, because we're really interested in pH, we're kind of interested really in just this guy right here, this sort of part of it. So when we solve for X a lot of times in a weak acid problem, that should equal the H plus concentration. So when you solve for that X, that should be the H plus concentration, and that's what you need to get to the pH. So we do just like we did in the previous chapter there with equilibrium. We make an assumption if you can make an assumption. If you can't make an assumption, then you need to do quadratic. You solve it just like a normal ice table. The only difference is we're usually interested in just the H plus concentration. That then goes into the pH equation at the end, and that allows us to get to the pH value. Any questions on that? Okay. Here's a table of just some weak acids, and again, you'll see some Ka values. We'll talk about this a little bit later, but this is a guy that has 3 H's that will come off. That's what is referred to as a triprotic acid. And there's actually, as we talked about, the H plus comes off one step at a time, right? In that stepwise fashion. And there's actually 3 K values associated with each of those hydrogens that basically come off. Here's carbonic acid, has 2 Ka values associated with it, 1 for each of the hydrogens, and so forth as we come through here. Here's some more. Again, here's some of these monoprotic acids. Obviously has just 1 sort of Ka value associated with it. This is hydrogen sulfate, and even on this table, they don't have the H2SO4 listed because it's considered strong. And usually in a lot of tables, it'll just say large or something next to it. And then it'll have this value here for the second hydrogen that comes off. All right, so here's a few more, and we'll get back to some of these here. Why don't you give this a go? Why don't you calculate the pH here of a 0.5 molar HF solution. And let me give you the Ka value to use for HF. Ka value is 7.1 times 10 to the minus 4. So why don't you give this a go, see what you come up with, take a few minutes. Here, you want to approach it just like a normal ice table. equilibrium type problem. Again, the difference here is we're looking for pH. So at the end, you want to really go into the pH expression or equation there to calculate. So take a few minutes, see what you come up with, and then we'll talk about it. A couple of things. If you don't know, HF is a weak acid. Most of the time, you'd probably be given the Ka value in the problem. If not, then obviously if you went to the table and saw a Ka value for it, that should automatically tell you that this is a weak acid. And because it's a weak acid, it should automatically sort of point you in the direction of I should probably be doing an ice table. So when we do our ice table here, we're just going to write really the dissociation of our weak acid. And again, here, I'm going to leave the water out and just go with the H plus and the F minus. And then we pretty much kind of approach it like normal. We're going to do our initial, which is 0.5. We're going to go 0 and 0 here. We'll go with a change of minus x, plus x, and plus x. And here at equilibrium, we would end up with 0.5 minus x, x, and x. I think there was supposed to be a 0 there. We'll squeeze it in. Any questions on sort of the ice table setup? Hopefully you could kind of see it's very, I don't want to say very similar. It's pretty much the same as a normal ice table that we would be doing here. Any questions on that setup there? We could also write an equilibrium expression for this guy, and this would be just like a normal equilibrium expression. It would be our products divided by our reactants. And again, since it is an acid, a weak acid, this is what is referred to as a Ka value, and that would equal 7.1 times 10 to the minus 4. At this point, just like we do in a traditional equilibrium problem, we're going to take our equilibrium line here and basically put it into our Ka expression, and that would get us x squared up on top. 0.5 minus x would equal our 7.1 times 10 to the minus 4. Now we do have 7.1 times 10 to the minus 4, which is considered a small value of K. So just like in our equilibrium problems, we could give it assumption a try if you like. You could assume x is equal to 0. Remember that when we assume x is equal to 0, we cannot kill all the x's. Otherwise, you have nothing to solve for. Again, it's really just the x we're going to be kind of subtracting from a number or adding to a number. That would get us x squared divided by 0.5 is equal to 7.1 times 10 to the minus 4. I'm going to multiply the 0.5 to the other side. I then will also take the square root of it. And it looks like if we do that little move there, little square root action here, going to get us an x value of 1.9 times 10 to the minus 2. Also important that when we do the assumption that we check it, right? So we don't want to forget to check our assumption. So to check it, we take the x value that we got. We then divide it by what we were going to subtract it from, which is usually the initial concentration. And we times it by 100%. And if we do that, looks like we're at like 3.8%, which means this is a good assumption. Remember, we're going to be using the 5% rule here in this class, so that's good, but always important to check it, especially in acids and bases. You'd be surprised how many times it might not work right for you. So because the assumption is good, what that means is, again, if we kind of look at our ice table to figure out, what is going on, we're really interested in the H plus, which does equal X here at equilibrium. So that means that that value right there is our H plus concentration, which technically means it would be molarity. And that means we could go right into our pH. It looks like we end up with a pH of 1.72. That is acidic, which makes sense since this is an acid. So that's good. Any questions on any of those sort of steps there? So again, I remind you that, if you do make that assumption, you want to make sure you do check it. And again, always you should check it, but definitely here in some acid and bases, there will definitely be times where it will not work or be correct. Any questions on where any of the numbers came from or anything like that? Okay. So just to sort of touch upon that point again, if we did the same problem, exact same problem, except that we kind of just lowered the concentration from 0.5 to 0.05, just to show you everything again, pretty much everything would be the same here that we just did. Except initially here, this would be 0, 5, 0, 0, change minus x plus x plus x. Again, everything exactly the same except for that concentration. And what that would get us is x squared over 0.05 minus x is equal to 7.1 times 10 to the minus 4. Here, if we made the assumption of x is equal to 0, we end up with something like maybe, we'll call it 6.0 times 10 minus 3. And if we check our assumption in this case by dividing it by 0.05 times it by 100%, you get roughly 12%, which means this would be a bad assumption in this case. And again, that's why it's really important to make sure that you do check it. It looks almost identical. But as you could tell, the concentration here is about, 10-fold less. So because we have a smaller starting concentration, the change part here is significant in this case versus where we had the larger H plus concentration or HF concentration to start with. The change was not so significant in this particular case. It's kind of like, we'll talk a little bit about it later, but, kind of like, you got a whole like pizza, right? And you just take one piece out, you still have a lot left. It's not that big of a deal, but you're down to maybe, you open the box and there's only like, maybe one slice or maybe two slices. And somebody takes the same one piece, right? That makes a much bigger difference, right? In the overall change that you had versus who was the first slice there off of the pizza box. So concentration is a really important part of it, as we'll talk about as we go through this chapter, that, depending on sort of your initial concentration, sometimes your assumption may not work because of that. You're starting with a very small piece of the pie, if you will. And if you take a little bit of that small piece, it's going to be a pretty big change that's occurring, as opposed to if you had a bigger piece that you're starting with and you take just a little bit out of it, it's going to be not as big of a change. Any questions on that there? So as we sort of saw here in this example, we really do solve these weak acid problems or Ka problems pretty identical to how we approach a normal equilibrium problem. Really, the main difference is we are looking for really kind of the H plus concentration at the end so that we can simply put it into our pH equation. So again, you want to approach these the same way. Just like before, if you want to do the assumption, you can. If it works, it's good. If you want to skip the assumption like we talked about in the equilibrium chapter and go straight to the quadratic, you could do that too. Should get you the same answer, maybe slightly off with some rounding. All right, so why don't you try another one here and see what you come up with. So take a couple of minutes, and here we're looking for a pH of a monoprotic acid, whose Ka value is 5.7 times 10 to the minus 4. If you're not sure what to use for the formula, monoprotic means 1H, so this is like the generic formula of a monoprotic acid. So you can use that. All right, so take a few minutes, see what you come up with, and then we'll go over it. At this one here. So again, if you're not really given a formula of a specific weak acid, you know, this is a good one to use. This again represents really a sort of monoprotic acid. If you had diprotic, you know, it would be H2A. If you had, say, triprotic H3A, the difference is on this side, you would have 2 H pluses and the A would be 2 minus. This guy would be 3 H pluses and the A would be 3 minus. So, you know, these are sort of ways you sometimes can just use sort of generic formulas. So we'll use these guy here, a monoprotic. So we'll just kind of have our guy again breaking apart into H plus and A minus. We're going to do an initial ice table here with our 0.122. It's going to be 0, 0. Change will be minus x, plus x, and plus x, which means at equilibrium 0.122 minus x, x, and x. Any questions on that so far? We can write our equilibrium expression here, which again is our Ka. By the way, this is how we know we should have a Ka we're using, because there's H plus on the product side, which basically signifies an acid. This is going to give us H plus A minus divided by HA, and that will equal our 5.7 times 10 to the minus 4. Putting our numbers in there, that's going to give us x squared up on top, 0.122 minus x on the bottom, equals 5.7 times 10 to the minus 4. Here we could assume x is equal to 0. That gets us x squared over 0.122 is equal to 5.7 times 10 to the minus 4. Finding my calculator, what did I do with that thing? There it is. Taking our 0.122 to the other side and times it by 5.7 to the minus 4 and taking the square root of it, going to get us an x value here of 8.3 times 10 to the minus 3. We want to check it by dividing that by 0.122 times it by 100. And if we do that, we end up with 6.8%, which is greater than 5%. So this would be a bad assumption in this case. So again, a good reason why you should not just blindly go with the assumption all the time, because it will not work out. Some cases may not be that big of a difference, but we will use that 5% rule. So again, technically speaking, this is not correct. That means we need to again step back to pretty much here and really solve it another way, which is our quadratic. So that would kind of back us up to x squared over 0.122 minus x equals 5.7 times 10 to the minus 4. We're going to multiply everybody on the bottom to the other side. That's going to give us x squared is equal to we'll go with 6.95 times 10 to the minus 5, so I don't have so many zeros, minus 5.7 times 10 to the minus 4x, bringing everybody to the left-hand side so everybody's on the same side there. That's going to give us x squared plus 5.7 times 10 to the minus 4 minus 6.95 times 10 to the minus 5 would equal 0. That is going to be what we need for our quadratic, as this here would be A, This would be B, and this would be C in that particular case. Any questions on that so far? Quadratic, it's like we've done before, is minus B plus or minus the square root of B squared minus 4AC divided by 2. Kind of putting some numbers in, that takes us to minus 5.7 times 10 to the minus 4. Plus or minus, and then putting our numbers there in the square root. We're going to take our B squared times our 4 times A, which is 1, times C, which is minus 6.95 to the minus 5. So I think inside the square root, if I'm not mistaken, you end up with something like, we'll go with 2.78 times 10 to the minus 4. And if we do a little square root action of that, going to get us, I believe, 0.0167 on the square rooting of that, divided by 2 times A. A is 1, so that's going to give us 2. That should get us 2 separate answers like we've seen before. So doing the plus here, divided by 2, gets us something like an X value of 0.00. We'll call it 81. Or if we go negative, which is probably not going to be a good answer for us, or the subtracting, I guess is a better way of saying that, going to give us a negative value of minus 0.0086. In this particular case, negative will not work because we are looking for the H plus concentration. That means that this guy here should be our actual X value, and that means that the H plus concentration will equal our 0.0081 molar, which means pH in this case minus the log 0.0081. Going to give us a 2.09 in terms of our pH value in this particular case. Any questions on where any of those numbers sort of came from? If you did the assumption and blew right by it, you actually, in this particular example, probably got a number pretty close to that. But it would technically be wrong because, again, that assumption would be too big. So it may not make a big difference in some cases, or it may make a pretty big difference in terms of what you got. Any questions on any of those steps there? So again, in our case, because the thing was over 5%, you did need to go back and solve it the other way. Question on weak acid problems or Ka type problems. Again, pretty much the same thing as equilibrium problem. Only difference is kind of at the end there, we go into our pH.
And then for the quadratic formula, we can just get rid of any negative answers. That doesn't make sense.
Yeah, probably in sort of a weak acid type problem, you probably could, because in most cases, especially if it's monoprotic, your H plus will usually equal X, which means obviously you can't have a negative concentration and really won't work in this case. So probably in most cases, the negative is probably really the wrong one because of that specifically here in this application, because you got really these two guys that are just X. So you can't really have a negative concentration at the end. So you want to go with the positive one. Other questions?
Right,
You're welcome. Other questions? Okay. So let's talk also about sort of another application here of weak acids, and this is what is known as percent ionization. Actually, no, let's do one more problem here. I'm sorry, I jumped the gun. So give this one a go here and see what you come up with. Calculate the H plus, and let's also do the pH as well. So let's get the pH here of this guy here. Ka value given to you, see what you come up with, and we'll check on each other here in a second. Ka value here. We know this is going to be weak. We also know we will need to kind of set up an ice table here. So it's just going to be our weak acid dissociating into H plus and Cn minus in this case. Initially here, we got 0.01. This will be zeros. Change minus x plus x plus x, which means at equilibrium 0.01 minus x, x, and x. Any questions on the table here? If I get that x there. We also could write our Ka expression for this, which would again be our products divided by our reactant. And that would equal our 6.2 times 10 to the minus 10. Putting in our values into there gets us x squared divided by 0.01 minus x is going to equal 6.2 times 10 to the minus 10. Here we will assume x is equal to 0. Gives us x squared divided by 0.01 is equal to 6.2 times 10 to the minus 10. We're going to multiply the 0.01 to the other side. We're going to take a square root of it, and it will give us an x value here of, we'll call it 2.5 times 10 to the minus 6, I believe. If I counted that right, zeros, 1, 2, 3, 4, 5, 6. We do want to check it. So again, we'll take our 2.5 times 10 to the minus 6 divided by 0.01 times it by 100. And in this particular case here, we are good. We're not even near 1% even. It's like 0.02%. So this is a good assumption. That means that this would equal our H plus concentration coming through here, which also means the answer here would be 2. And we can now calculate our pH, which would be minus the log of 2.5 times 10 to the minus 6. And that's going to get us minus the log 2.5 to the minus 6. Looks like a 5.60, which is still acidic. Any questions on any of those steps here?
So if we were to use the quadratic formula, we would essentially get the same answer?
Yeah, you should. You should really get the same answer if you just went straight into the quadratic formula, which you could definitely do. And again, maybe slightly different depending if you did a little bit of rounding with that quadratic, but you basically should get the same answer at the end. It shouldn't, for example, you shouldn't get something like at the end, like 2 point something for the pH or something like that. So, you should be in the same ballpark. Maybe you get like 2.6 to the minus 6, or, maybe 2.4 or something, depending on rounding, or even 2.5, but technically you should get pretty much, as long as you didn't do a lot of extreme rounding along the way, you should get pretty much the same answer at the end. Other questions? And again, it is a preference. Sometimes people, especially if they've had a run of maybe assumptions that don't work, they just decide I'm just going to go straight through with the quadratic. Again, it obviously could save you time by doing the assumption, but it definitely should get you the same answer, regardless of sort of which way you go. Other questions on that? Okay. Other questions on weak acids here? All right, so now we get to what I was going to talk about. So another sort of aspect of that we look at in terms of weak acids and so forth is what is sometimes referred to as percent ionization. Percent ionization for an acid is really the how we check our assumption. If you think about how we check our assumptions, when we do make those assumptions, we usually take the concentration of H plus, which is what we get for X, and we divide it by the initial concentration, and we times it by 100. So when we're really doing our sort of check of our assumption, when we assume that X is equal to 0, what we're really doing at the end is calculating what is known as the percent ionization. And the idea there is if it's, less than 5% ionized, the change is not going to be that much. But if you start to get into a percent ionization that's greater than 5%, really, then the change is significant. And that's sort of where the 5% rule sort of comes from, is actually where we are calculating what is referred to as the percent ionization of an acid. Ionization is just a fancy word for basically the thing breaking apart into ions, right? And that's basically what an acid does. What makes something an acid is the ability to produce H plus free in the solution. Strong acids have 100% ionization. As we talked about, they're a one-way street. They're going to 100% break apart. Weak acids, on the other hand, has a very high percent ionization when concentration is low or small. Percent ionization gets a little bit smaller when the concentration of the acid is large. So that's sort of what I was talking about earlier when I kind of did the pizza example. You know, if your initial concentration of your weak acid is large, you got like all the entire pizza and somebody just takes out a slice, you know, it's going to just be a little bit of change that's occurring there, or percent ionization. But again, as we talked about, if you just have the, you know, the two pieces left there in the box, you know, that kind of puts you over in this range in terms of its initial concentration. So when somebody grabs out one piece, it's a much bigger percent ionization that's occurring and a much bigger change that's occurring. And really that change is that X sort of value that we do in the ICE table, you know, when we calculate it. So to calculate the percent ionization, it is this formula here. You basically take the concentration of H plus that's in the solution, you divide it by the initial concentration of the acid, that's what the little circle there on the bottom means, or O, and times it by 100, and that will give you your percent ionization for your particular acid. So let's take a look at this problem here together and sort of see how we could use this type of information to help us calculate maybe something like a Ka value. So in this particular case here, we have a solution that's 8 molar formic acid. It is 0.47% ionized. What is the Ka value for formic acid? So we obviously know formic acid is a weak acid because we're looking for a Ka value. So if we kind of approach this problem like a traditional weak acid problem, what we would do is we would set up our ICE table here, where our formic acid would drop a H plus and make something like this, perhaps. And initially we have 8 molar. This would be 0, this would be 0, this would be minus X plus X plus X. This would be at equilibrium 8 minus X, X, and X. So if we did an ICE table like normal, we would kind of put in our numbers, again, this being our initial concentration here. We would have a Ka expression, which would equal H plus times HCOO minus divided by HCOOH. And that equals, in this case, I'm not sure, that's what we're looking for. So at this point, we have a little bit of a situation because normally we take these guys and we put it in here and we solve for X. But obviously in this case, we're looking for actually what is the value of the Ka. So what piece of information will help us do that? It's actually the other piece of information that was given to us in this problem. It basically tells us that this acid is 0.47% ionized. So if we think about the formula that we just saw for percent ionization, the percent ionization is equal to the H plus concentration divided by the initial acid concentration times 100%. Well, we know the percent ionization is 0.47%. We don't know what our H plus concentration is, but we do know what our initial concentration was, which is 8 molar times 100%. What that's going to allow us to do is solve for H plus. H plus would equal really 8 times 0.47%. divided by 100%. What are we really doing here? We're really taking 0.47% of 8. That's what we're doing. You could also just done it by moving the decimal point over 2 places on 0.47 and then times it by 8. But if we do all this here together, we end up with an H plus concentration of 0.0376. So using the percent ionization that was given to us in the problem, we can use that formula to calculate what the H plus concentration is. First off, any questions on that calculation there? Why would knowing the H plus concentration be important? Well, if we go back to our ice table, we see that the H plus concentration at equilibrium equals X. And now that we know that the H plus concentration is 0.0376 molar, we now have the value of X for our ice table. And that X value is this X value. That X value is obviously this X value. And that X value is that X value is there. So now we pretty much have all the numbers we need to actually calculate our Ka. Our Ka should be X on top for H plus, which is 0.376, times our formate, which is also X, 0.376, divided by our formic acid at equilibrium, which is 8 minus X, which would be 0.0376. I feel like I lost a 0 there on those, so we put a 0 in there. I'll fix those real quick here. Sorry about that. I think I lost me a 0 there. Not a good idea. So that's going to be 0.0376, and that's 0.0376. That then gets us, if we do that, that's basically squaring the top divided by 8 minus 0.0376, going to get us a Ka value of, we'll call it 1.8 times 10, and that is 1, 2, 3 minus 4. Any questions on that calculation? So in this particular case, because we were not given enough information, obviously, to solve it sort of traditionally, that piece of information about the percent ionization is really important. It allows us essentially to sort of work backwards in this case, right? We could kind of work backwards to get our X values here from the percent ionization, and obviously allow us to calculate the Ka value in this particular case. Any questions on that there? Okay, so that is percent ionization, basically the amount of H plus that's in solution that's free, floating around, divided by the initial concentration of the acid times 100 gives you that percent ionization. Obviously, if something has a very high percent ionization, then it's broken apart a lot, right? If something has a low percent ionization, then it is not broken apart. So we've talked about weak acids. So of course, what would come next is weak bases. So we do have weak bases. They work just like weak acids. They also work just like equilibrium problems. Because they are weak bases, they do not 100% break apart, but they do set up this equilibrium. And in this particular case, the ammonia is our base, and it's going to accept the H plus from the water. And in these reactions, I would include the water in there. Doing our Kb, again, products over reactants. This guy does not get included because he is a liquid. Gives us our NH4 plus over our OH minus, our times our OH minus divided by our NH3. This is what is referred to as, surprisingly, a Kb, B being base, right? And so this is a weak acid, weak base equilibrium constant. I'll spit that out, right? A weak base equilibrium constant, again, because it is dealing with the base here. Works the same way, sort of the same idea. The greater the Kb value, the greater the strength of that weak base. And again, it's for the same reason. If you have a large Kb value, that again means you have mainly products. If you have mainly products, that means you have a lot of free OH minus floating around. That free OH minus means it's basic. And that's why we sort of see it as a stronger weak base. Just like with our acids, if you're comparing a weak base to a strong base like sodium hydroxide, potassium hydroxide, something like that, obviously the strong base is much stronger than a weak base. Again, for the same reasons we talked about, it will 100% break apart into ions, produce a lot of OH minus in the solution very quickly. How do we solve these problems? Well, we solve these problems the same way as we do weak acids, except that because when you look at the equation, and it's important to be able to write these equations correctly, you will find yourself on this side with OH minus rather than H plus. And that OH minus means that you need to first go into the POH at the end of your ice table and then into your pH. So maybe an additional step along the way. Any questions on that there? How do we know if we should be using at this point like a Ka value or a Kb value? Well, obviously one's for an acid or one's for a base, and sometimes people may not be able to recognize what they're dealing with, perhaps. So again, it's really important to be able to write these equations correctly. And the way you could always know sort of, which one you should be using is when you write the equation properly on the product side. If you have H plus or H3O plus there, you should probably be using a Ka value for your calculation. If on the product side you produce hydroxide like we see here, you should probably be using a Kb value. So it's really important to be able, again, to write these equations and also be able to recognize what you got going on. There will be problems coming up in this chapter where, I won't say it, I guess I'll say it this way. They will give you the wrong K value. They'll give you a Ka value when you need to use a Kb value or a Kb value when you should be using a Ka value. So that's why it's extremely important to sort of understand how to write these equations properly. And that's sort of a simple way to look at your properly written equation. And if you look on the product side, you see H plus or H3O plus, probably an acid type problem, probably should be using a Ka value. If you see hydroxide there on the product side, probably a base type problem and should be using a Kb problem. Any questions on that there? Here's a table of some Kb values as well. And obviously, if they're not provided for you, you might have to look them up in a table. Same thing with our acid. We could recognize something as a weak base because it has a Kb value associated with it. So we will not see strong bases have Kb values for the same reason as strong acids. Strong bases will 100% break apart into ions, will not set up an equilibrium, thus they do not have a Kb value. Weak bases will set up that equilibrium and will have that Kb value. So why don't we finish up here on this guy here, give this one a go. We have this guy here at Kb value of 5.6 times 10 to the minus 4. What would be the pH of a 0.15 molar solution of this base? So see what you come up with, take a few minutes, then we'll talk about it and see how everybody's doing. Okay, since we're getting kind of to the end here, let's take a look and kind of see how we do this. So a couple things, obviously we see a Kb value, so that definitely tells us we're dealing with a weak base. Also tells us that we should be doing some type of ice table to solve this. So this is a base. So our equation will look something like C2H5NH2. And when you're dealing with a base, it's a good one to put the water into the equation. And because it's a base, it's going to accept the H plus from the water. And when it does so, we'll get like C2H5. I'll just put the extra N at the end. And we also will have a plus that will occur in this particular case. when the water kind of loses the H plus, it makes the OH minus, which is again what we should have on that side, as we just talked about, because we're dealing with a KB problem. I can't tell you how many times I've seen people write an equation like this, or I guess I should say, attempt to write an equation like this, and we'll end up with H3O plus on the other side. And that is not good, because then you will get the wrong answer, because you won't get obviously the right calculation. You might get the right number, but at the end of the ICE table, you'll think it's the H plus, and you'll go into the pH equation and obviously not get the right answer. So very important to be able to write these equations correctly. It just helps with the calculation part a lot. Any questions on that? At this point, we're going to really approach it like we've been doing. We're going to go with 0.15, 0, and 0. Change would be minus x, plus x, and plus x. And 0.15 minus x, x, and x. Again, here, water not going to be included in the equilibrium expression, which is why I didn't put anything in this column here, so I don't try to use it in a wrong application. This would obviously go into our KB value. Again, we know it's KB because we see OH minus on our product side. That gets us our x squared over 0.15 minus x would equal our 5.6 times 10 to the minus 4. Any questions on the ICE table or anything up until this point? We're going to go with the assumption that x is equal to 0. That will get us x squared. 0.15 is equal to 5.6 times 10 to the minus 4. Multiplying the 0.5 to the other side and also taking the square root of it is going to get us some disappointment, I'm thinking, but we will end up with an x value of 0.00917. Again, we want to make sure we check it here. And if we do check it by dividing it by that 0.15 and times it by 100, that is a 6.1%, which is not good in this particular case. So this technically is a bad assumption. So again, make sure that you do check it and not just blindly roll with it and hope for the best. Any questions on that there so far? That means obviously we need to go back here to basically this and solve it our favorite way, which is the quadratic. So I'm gonna go this way, and I need somewhere to scribble. So let me, actually here, I'll just do it here, not right. I'm just gonna rewrite here. We have, what did we have there? Go back, x squared 0.15. So we have x squared over 0.15 minus x is equal to our 5.6 to the minus 4 there. All right, so multiplying everything on the bottom to the other side, going to give us x squared is equal to 0.15 times 5.6 to the minus 4, going to get us an 8.4 times 10 to the minus 5 minus 5.6 times 10 to the minus 4x. Going to bring everybody to one side, going to give us an x squared plus 5.6 times 10 to the minus 4x minus 8.4 times 10 to the minus 5 is equal to 0. That is going to give us our A, B, and C going on here. And C. That's going to give us our x is equal to minus b plus or minus the square root b squared minus 4ac divided by 2a. Popping in some numbers here, minus b would then be minus 5.6 times 10 to the minus 4 plus or minus. Again, if we kind of clean up what's inside the square root, I believe you end up with something like 0.000336. Upon square rooting that ends up with 0.000336. 0.0183339, not doing a lot of rounding there, divided by basically 2 in this case. Just like we've seen before, this will obviously yield us 2 different x values. So we'll do the plus part first. So that's going to be minus 5.6 to the minus 4 plus 0.018339 divided by 2, going to get us an x value of 0.00889. Are going with our subtract there. And actually punch it in right, 0.018339. And divided by 2 gets us a negative 0.00945. A reminder here that we were, if we look at our table here, we are looking for the OH minus concentration, and that equals X. So just like we talked about before, that negative value is not going to help us here again, because that obviously would give us a negative concentration. That means that this guy here, X should equal 0.00889 molar, which would equal the OH minus concentration. So again, like I was talking about earlier, it's really important to write this equation correctly, because if you wrote it incorrectly at this point and you had H plus or H3O plus here, you would think that that's the H plus concentration and go into the pH equation at this point, and that would obviously give you the wrong answer. Because it is the OH minus concentration, we first need to go into the POH, which would be minus the log of the OH minus, and that would be minus the log of 0.00889. That's going to get us, looks like maybe a 2.05 for our POH, remembering that the pH plus the POH is equal to 14. That means the pH here would be 14 minus our 2.05. Gives us a pH of about 11.95. And that pH does make sense, as that is basic. And since we're dealing with a base, that is probably what we would expect it to be. Any questions on any of those steps there? Again, hopefully you could see sort of a pattern here. These are really just equilibrium problems with an additional sort of step at the end where we try to get the pH. So either go directly into the pH in a weak acid problem, or you kind of go POH to the pH here in a weak base problem. But again, really important to be able to write these equations correctly and understand, what you should be kind of doing and what you should be expecting. And again, if you messed up earlier, like I was talking about, and you thought that the X was the H plus concentration, again, the understanding that this is a base, that number would not look like a basic pH if you kind of messed up in terms of that earlier. So it's really important to write these equations correctly and sort of understand what is happening. Any questions on that there? Okay, we will stop there for today.